Hi there, this is Physics, the chapter on transfer of thermal energy, Lesson 2, Conduction. Now in this lesson video, we will deal with the physics concept of how thermal energy is moved from one place to another by conduction. Before we move on, I would like all of you to keep something in mind again, the kinetic theory of particles from the previous lessons. Recall that this theory states that particles are always in constant motion, and furthermore, recall how the particles are arranged in solid, liquid and gas states. And when I say this, I hope phrases like vibrate about fixed positions and closely packed comes back to mind. What you have learned and understood from the kinetic theory will provide the base from which you will understand the ideas of conduction. Now, before I move on, let us revisit the learning objective for this particular video lesson on conduction. We are going to be able to answer these three key questions. First, conduction heat transfer. How does conduction work? Second, conduction happens best in which state? And third, is there a difference between conduction in non-metal solids and metal solids? So let's find out what conduction is all about. Now, conduction heat transfer is a method of heat transfer through a medium without any flow of the medium. To understand this statement, let's have a look at this diagram. This diagram shows a solid object, a rod with one end near to the flames of a Bunsen burner. Well, you know that after some time, the heat that is gained at this end of the rod will travel slowly up the hot end, from the hot end to the cold end of the rod. This heat moves by conduction, which is via the vibrations of atoms and molecules which make up the rod. Sometimes we use the general term particles to refer to either atom or molecules too. So do not be surprised when you hear the term particles from now on. So what does it mean by without any flow of the medium? As you can see, while heat travels towards the cold end, the material that makes up the rod itself does not move upwards. It stays where it is. So how does the vibration of particles help in the transfer of heat? Now in this particular slide, we will zoom into the rod itself. Now this rod is a solid. Therefore, it is made up of particles which are arranged in systematic order, and notice that they are also very closely packed. Recall also that these particles move continuously. In fact, when left alone, they are vibrating about a fixed position. Now, when particles near to the flame gains heat, they will vibrate more vigorously than before. And as a result, there's this chance where they will collide with their neighbors. During these collisions, heat is transferred from the more vigorous particles to those which are less vigorous. So let's have a look at the animation here. So if we continuously supply the heat to this rod, these particles will vibrate a lot more vigorously compared to those at the cool end. So when they vibrate more vigorously, they will collide with each other and hence transfer energy or heat from these more energetic particles to the next one, and so on and so forth. So this is how heat is being transferred by conduction in a solid material. So conduction happens very well in solids, since the particles in solids are very closely packed. The question now I would like to pose to you is, do metals and non-metal solid conduct heat equally well? I bet you know the answer to that. For solid materials which are made from metals, for example copper and iron, there's something extra in these metals itself, in these solid metals itself. Apart from molecular vibrations, there are also free electron diffusion taking place, as only metals have free electrons. So in your chemistry subject, you probably have learned about free valence electrons. So metals have these free valence electrons, and these electrons are free to move about. So for metals itself, electrons which are nearer to the heated end, for example, will also gain energy. And this energy will cause these electrons to move faster. And when they move faster, these electrons gain kinetic energy. And as they move faster along the length of the rod, these electrons which are more energetic can also collide into other particles. As a result, due to the collision itself, some energy will also be transferred to these particles. Now remember this as well. there are a lot of electrons which are free inside a metal rod. So as a result, all these electrons which are very highly energetic will start to travel down the length of this rod. And as they travel down, when they collide with the particles, some of this energy will be transferred to the particles as well. So there we have it. It is the presence of these free electrons in metals which makes them a better conductor of heat compared to non-metal conductors. Now from this point onwards, we will be looking at 3 cases regarding conduction. Okay, and interestingly, GCE O and N levels examinations often evaluate students' understanding on this conduction from these few cases. So do try to listen in, yeah? Now, this is a particular experiment in which we use to investigate which solid material is a better conductor of heat. In this example, we see that there are 4 rods of the same size and length are placed in a tank of hot boiling water. Each rod is coated with candle wax. So after some time, what can we conclude about which material is the best heat conductor? Well, from the diagram, we can see that copper has a lot of wax melted off, followed by iron, glass, and wood. This therefore suggests that copper is a better conductor of heat, since heat can be transferred rapidly from the tank of hot water to the other end of the rod. The faster the heat is transferred, the quicker the rise in temperature of the rod. Hence, wax around the copper melts more quickly, okay, compared to the others. So from this experiment, we can also tell which material is the best thermal insulator, and that would be wood. So which rod will have the longest length of wax remaining after some time? Well, the answer to that would also be wood. Now let's recall that in the last few slides, we have been discussing conduction heat transfer in solids. The question now is if conduction can also occur in liquid or even gas. This experiment over here proves that conduction can also occur in liquid, but we'll find out that liquid is a very poor conductor of heat. Now this experiment shows ice wrapped inside metal wires. Okay, when this ice that is being wrapped in metal wires or metal gauze is placed inside a boiling tube with some water, it will sink right to the bottom. Okay, now let's say that this boiling tube is being placed on a Bunsen burner. Okay, the flames of the Bunsen burner just touching water at the top of the boiling tube at this particular location. Interestingly, after some time, we will find that the water near the top will start to boil. We in fact will see bubbles around here, suggesting that the temperature of water at this point has reached 100 degrees Celsius. However, if we zoom into the ice cube, we'll find that the ice cube is still present, but melting very, very slowly. So why is that so? The explanation lies in the kinetic theory of liquid state. In liquid state, particles are not as closely packed as solid. And furthermore, they are able to slide freely around each other. So when particles at the top of the tube gains heat, these particles slides around more rapidly with only some small collisions with their neighbors towards the bottom. As a result, only a small amount of heat is transferred due to collision between particles. So in conclusion, water is therefore a poor conductor of thermal energy. So if water, which is in liquid state, is a poor conductor, we can therefore conclude that liquid in general are also poor conductors of thermal energy. Now let's have a look at this last case. Okay, when a Bunsen burner is lighted from above a wire gauze, this is a wire gauze, alright, the flame stays above the wire gauze instead of at the barrel. Now how do we explain this phenomenon? Again, this tells us that metal is a very good thermal or heat conductor. Therefore, the heat of the flame is conducted away rapidly to the metal gauze, and the temperature under the gauze is not enough to ignite the gas, which is why we can find that the flame appears above the wire gauze rather than at the barrel. Okay, so that brings us to the next slide. From the previous three examples, we have seen that conduction heat transfer can occur not only in solids but also liquids. How about gas? Can conduction occur in gas state as well? Well, if you think they do, well, you are right. As long as the more energetic particles, whether in solid, liquid or gas state, as long as they can collide with each other and pass on some heat or thermal energy after the collisions, conduction can certainly happen. The key is conduction is highly effective when particles are closely packed, so solids are the best conductors of heat. Liquid and gases, collectively known as fluids, are poor conductors of heat simply because they are not as closely packed as solids. The worst between liquid and gas would be gas. Gas is the poorest conductor between these two states. So sometimes instead of calling them poor conductors, we call them insulators. So now we have found out that gases are poor conductors of heat. Do they have their use as well? Of course they do, right? For example, woolen clothes and blankets usually are designed to contain large amount of trapped air. And air, being a very poor conductor of heat or a very good insulator of heat, does not allow heat energy to flow outward from our body. This will then keep our body warm. Now we know how conduction occurs. Scientists and designers and engineers have come up with ways and means to make use of conduction in the design of everyday stuff. Now in this particular slide, we see two items that is very common to our household. First is a steamer, and the other one is a double glazed windows. We don't often see this in the hot tropical climate of Singapore, but usually in those countries with 4 seasons. Okay, so what are the features that make them very good for our use, right? So let's look at a steamer. All right, the steamer is usually placed on table mat. Table mats, being non-metals, are very good insulators, and as a result, they will prevent heat from being conducted away from the pot onto the table, right? Now, we also see that plastic handles are designed, right, into this appliance in order to allow us to handle this appliance with care. Plastic, being a good insulator, prevents us or the user from getting burnt. So we also see that we use glass cover. Glass, being a non-metal, is also a good insulator. Now for the double glazed window, all right, what it simply means is that between there is a layer of trapped air between these two sheets of glass. Air, as we have learned, are poor thermal conductors, and as a result, this will reduce the rate at which heat is transferred across the glass, the two pieces of glass. All right, so this itself will keep heat within the house during the winter, and at the same time, it will keep heat out of the house during summer. Okay, now that basically brings us right to the next slide and the last slide for this video. So let's summarize what we have learned so far. We started off with 3 learning outcomes. The first being, how does conduction heat transfer work? Well, key idea here is that do remember that conduction occurs by molecular vibrations and collisions, and it is these collisions that energy is transferred. In metals, there's something extra. There is also this phenomenon called free electron diffusion. Conduction happens best in which state? Well, we have learned that conduction can happen very well in solids, but it can also occur in fluids, which is liquid and gas, and also between solid and any fluids. Is there a difference between conduction in non-metal solids and metal solids? Yes, indeed. Metals are better conductors of heat, while non-metals are not, and they are usually called insulators. Right? And with that, thank you very much.